Where are we at today, Vin?
Today, we're at Tulane University's Paul Hall, a brand new state of the art research facility that puts science on display.
Our guest is Dr. Bolu Ajiboye, a professor in the Department of Biomedical Engineering at Case Western University. And his research focuses on restoring sense and mobility to limbs by reconnecting them to the brain and bypassing damaged nerves.
This is Big Easy Science.
So my name is Dr. Bolu Ajiboye. I'm a professor in biomedical engineering at Case Western Reserve University. I'm also part of the Cleveland Functional Electrical Stimulation Center, which is at the Lewis Stokes Cleveland VA Medical Center. For the past 30 or 40 years, the VA FES Center has been developing implantable medical devices to restore movement to people with paralysis because of spinal cord injury. And these devices essentially work by applying small amounts of electrical stimulation to the muscles and nerves in the paralyzed limb. And then by coordinating that stimulation, you can produce functional movement, like reaching out and grasping objects. Now, what my lab specifically focuses on is giving the control of that, what we call a neuroprosthesis, back to the user so that they can use their native brain signals to control that functional electrical stimulation or FES system. So the way they control it is using a brain-machine interface, a BMI. You also hear the term BCI, brain-computer interface. And essentially what this consists of is using electrodes, in our case, that are implanted inside the brain, which allow us to record brain signals at a very high resolution. We're actually sampling the brain at 30,000 times a second. We essentially are recording the activity of individual brain cells called neurons, and then we're looking at patterns of those neuronal activity and using techniques, standard statistics, machine learning to understand the language of the brain. And then once we can understand what those patterns that are generated in relation to movement are, then we can then stimulate the arm and the hand to essentially reconnect the hand and arm back to the brain, or rehab, the acronym.
And you said there are like two terms for this, both BCI or brain machine interfaces. Like, is there
Are they interchangeable?
They are generally interchangeable. Traditionally, the BCI, or brain computer interface, was the first term, and I think this stemmed from the fact that these initial devices. So initially, this work was pioneered in non-human primates, NHPs, and essentially you'd have a non-human primate with a cortical implant, with a brain implant, controlling a cursor on a computer screen, being able to modulate neural activity to move the cursor left, right, up, down. So hence brain computer interface. Since then, it's gone from brain just controlling things on the computer to controlling more complicated devices such as robotic limbs, which have more than the 2 degrees of freedom of a cursor. Our lab and our program has advanced the technology not just to controlling robotic arms, but now controlling the limbs of an individual who is paralyzed, who still has their limbs but has lost both the control of it and the ability to actually activate it. So my lab prefers the term brain-machine interface, because it's basically interfacing the brain with any type of external device, which goes well beyond the traditional computer.
It's broader.
It's broader.
Okay.
Definitely.
So when you first started doing this research, were you starting with the primate models, or had this already sort of been in a clinical or preclinical context?
Sure. So the field as a whole started off with non-human primate research, right? There are a number of seminal papers, seminal work, even from the 1980s, showing, and actually even earlier than that, the 60s, showing that non-human primates could modulate their cortical activity with the right biofeedback, visual feedback of a cursor or a line moving on the screen. They could modulate the activity of an individual brain cell to control that, or furthermore, populations of brain cells. And so that's kind of formed the bedrock and the foundation for now the human clinical work. I personally have never worked with non-human primates, but I do collaborate with other PIs who have NHP labs, and they essentially form like the preclinical model that allows us to, test different theories, different algorithms before translating it to our human participants. Since I've been in the field, I initially started off working with people with amputations. When I became a professor, I started working strictly with people with spinal cord injury. And again, we've been able to build off of the knowledge that's been well established in the non-human primate model, and now translated to people with spinal cord injury being able to use these brain-machine interfaces to control a number of external devices, including now their own limb through functional electrical stimulation.
So I know one of the things with just controlling your arm is that you're able to always feel when you're holding an object or something. But in these cases, can the people who have these BCIs have this similar sort of feeling when they pick up something with their prosthetic, or is it more of a visual cues with which they actually understand if they're picking things up?
That's a great question. So most people who have spinal cord injury have loss of both movement and sensation. About 30% of people with spinal cord injury do retain some sensation, so about 30%, and we call these people, they have incomplete spinal cord injuries. They may be motor complete, meaning they can't move, below the line of injury, but they may also be sensory incomplete, meaning they have some retained sensation. But a majority of people can be motor complete and sensory complete. And so the question is, in addition to restoring, the ability to move, how would we restore the ability to feel, to either tactile, so touch, or in some cases, in some cases, the ability to restore what we call proprioception, so the ability to know where your limb is in space without having to look at it constantly. With our current participants or previous iterations of this technology, the only feedback that these participants typically had was visual. They had to be able to look at their hand to know when they're touching or in contact with an object, look at their arm, know where it is in space, and visual feedback is actually pretty slow. About, the loop is about 400 milliseconds, 2 to 400 milliseconds, depending on who you ask. It's very, very slow. One of the goals of our current rehab program is to not just restore the ability to move, but also the ability to feel a sense of touch. And the way we do that is also through the brain-machine interface as well. So in terms of restoring movement, we are reading information from the brain. We're asking the neurons what they're doing, and then we're deciphering or decoding that pattern. When we want to restore sensation, we are going to be writing information to the brain. So we're going to be using small amounts of electrical stimulation, 100 microamps max, tens of microamps, to stimulate a part of the brain called the primary somatosensory cortex. And when you stimulate that part of the brain, you'll actually generate a sense of touch to the user. So if you stimulate the right part of primary somatosensory cortex, the person will indicate that they feel like you're squeezing their index finger, swinging their middle finger, ring finger, or thumb.
So when you're using these small impulses in the brain, what was some of the safety precautions that you had to think about? And also just, there's a lot of electrical activity going on, right? So how was that process finding the right level to get through all that different electrical noise there?
So let's talk about safety for a little bit. So the first thing that I'll say is that these devices require surgery. We actually just published a paper last year that went through the 25-year history of the 20 or so participants who received these implants, and have shown by and large that these devices tend to be safe. No unexpected adverse events. But it does still require a craniotomy, brain surgery. And so when this happens, the clinicians, the surgeons, researchers, patient safety, participant safety is the number one concern. And again, thus far, there's been an excellent track record of safety of the devices.
So just to add on, are these devices just superficially placed on, say, the brain, or is it a particular, or they go a certain deep into the brain, or how can you talk more
that's a
about
good question. So the devices we use are actually devices that are commercially made by a company called BlackRock Microsystems, and it's called a BlackRock microelectrode array, also sometimes called a Utah array, and it is a about 4 by 4 millimeter size array that has about 100 shanks on it. Again, it does penetrate cortical tissue, but about 1 to 1.5 millimeters in depth, so it's very shallow. The device then presently is percutaneous, meaning it has a pedestal which goes through the skin. People are working on making these devices fully implanted, but for now they're not fully implanted. But again, there is a strong history of safety, of both in terms of the surgery and then post-operatively as well. But now, in terms of defining safety parameters for using the device, so let's say, in terms of cortical microstimulation for restoring a sense of touch. There's been a lot of work done in non-human primates, which is established safety parameters in non-human primates again, that we then have adopted for our human participants. And all of this is fully regulated by the Food and Drug Administration. This device that we use, this Blackhawk microelectrode array, it is actually approved for what we call acute use, so less than 30 days. To leave it chronically implanted, we have to get FDA approval, getting an investigational device exemption or an IDE, and that allows us strictly for investigational purposes to implant the device for longer than 30 days. And so everything is very, very well regulated by the FDA. We have to report to the FDA any adverse events that may occur during the course of the study. But again, the safety parameters are also something that we had to define to the FDA to get our IDE, investigational device exemption, approved. And those are things that we strictly adhere to because, again, participant safety is the number one priority of our work.
So say everything goes well, there's no adverse effects. What does that timeline look like from, the device exemption, until clinical implementation? What does that, are we talking in terms of years, decades? What's that going to look like?
Yeah, so by clinical implementation, you mean in terms of like standard of care or something
Right.
that somebody could use it. So short answer is a long time.
Okay.
Short answer is a long time. We are using these devices purely right now for research purposes. Now, there is a path that we are following such that we can consider using these devices outside of our research labs and potentially even get users to use them at home, right? And so that is something we are presently working on, developing portable take-home versions of these systems so that people can think about controlling their arm at their home to complete, basic but functionally meaningful activities of daily living, such as feeding themselves, scratching their nose, things of that nature. But that's still done under the guise of the IDE, under the guise of the IDE.
It's still research.
It's still research, exactly.
Yeah.
It's still research. That's one thing that I will say, that what we're doing right now is we are not curing spinal cord injury. We are essentially circumventing the spinal injury, taking a detour, if you will, around the spinal injury to reconnect the hand and arm to the brain. Still research. Eventually, we would love for these devices to become standard of care, but there's a long road ahead. I mean, there are a number of technical and scientific challenges to overcome, and that's things that we're working on, other people in the field are working on. But there's also other challenges related to additional regulatory approvals, insurance, covering the costs of these things, et cetera. Commercialization, a number of things which are beyond the purview of academic research, but still critical in terms of having these devices have a chance of being standard of care.
I wanted to kind of go back to the percutaneous versus implantation.
Okay.
What would be the benefit for fully implanting the device? Is that purely an aesthetic choice, or would that improve the functionality of the device in some ways?
Sure.
What's the train of thought there?
Yeah, good question. So one is aesthetics, right? Second is safety, right? So anytime you have a percutaneous device, anything breaking the skin, there's always a risk of infection, right? And so when we are enrolling people in our studies, we are very clear and very transparent about any and all risks involved, and that there is an ethical responsibility to do so for your study participants. So having a fully implanted device will reduce objectively the chance for infection. Having said that, again, I'll say that based upon the 20-year history, there have been minimal adverse events related to infection or any other things, but there's always a risk. And so having a fully implanted system would minimize and mitigate that risk tremendously. So that's one. There's also the issue of, with a percutaneous device, the person needs to be connected, plugged in, if you will, to your external computers, external neural signal processors.
So there's an external device hosting all of that processing.
Processing all the data. The goal is to miniaturize that, and even if you could miniaturize it to the size of a cell phone, somebody would still have to connect this individual on a daily basis. We would like to get rid of that step, get rid of the process. We'd like to have these devices have the individual have as much independence as possible, and if they need to be connected and disconnected, that sort of reduces their level of independence. So having fully implanted devices could help. It would be a further step towards real independence of these users. Fully implanted does not necessarily mean wireless. You could potentially have tethered systems that are tunneled through the skin. That's a possibility. But depending on how you process your signals, you could have wirelessly telemetered connections between the brain implant and the implants in the peripheral arm to connect the hand and arm back to the brain.
It seems to me like the wireless connection might also pose some sort of cybersecurity risk as well, like being able to track that person's and take that person's brain activity data. Is there any possibility of someone being able to control someone's limb unwanted with some sort of cybersecurity attack to a device like that?
Yes, so security is always a concern, and fortunately there are people early on who are asking these exact questions and figuring out what the right protocols are. Similar questions in terms of ethics that people are thinking about right now, and it's never too early to consider those questions. Right now, to my knowledge, there aren't specific security protocols in place. It's not necessarily that things are fully encrypted right now, but when we move towards wireless protocols, and for sure that'll be part of the conversation, because again, our number one priority is safety, the autonomy of the individual, and making sure that they're not at risk of any sort of interruption or intervention that's unwanted.
So I kind of wanted to go back to talking about patients who have these spinal cord injuries, right? So of course, for long periods of their life after their injury, they probably have not used their muscles. And how does muscle atrophy now affect with your implementation of BCIs? Absolutely.
So muscle atrophy is a problem with with lack of use. Muscles will get weaker. They'll be more prone to fatigue and things of that nature. In terms of the FES, so functional electrical stimulation, that's the neurotechnology that we use to activate the muscles, right? And so one of the things that we need to do is, even prior to somebody using these FES systems, we actually exercise their muscles using cyclical electrical stimulation. So think about going to sleep, if they're asleep, and then we can just stimulate the muscles to sub-threshold, so there's not actual movement, but that stimulation, basically that exercise of the muscle, will increase its strength, reduce its fatigability, and then when we actually reanimate the limb in as part of our experiments, the muscle will be stronger and it'll be less likely to fatigue. Fatigue is a bigger issue in the lower extremity, so FES, electrical stimulation, has been used to restore lower extremity functions. And with lower extremity restoration, there's the need of load bearing. The legs have to be able to maintain the weight of the individual as they're standing, walking, transferring. And fatigue is a bigger issue than in the upper extremity. Part of the challenge with FES technology to date has been that the way that it recruits the muscles is actually, it's something we call reverse recruitment, okay? Native recruitment of motor units, so this is muscle physiology 101, as I like to say, smaller fibers which are more fatigue resistant but also produce less force get recruited first. It's what we call the size principle. Smaller fibers get recruited first, larger fibers, which are stronger, get recruited later. Okay, and so that way you're actually able to control fine motor forces, and then as the task requires more force, you recruit the larger motor units. FES, unfortunately, actually recruits the larger motor units first. And so what often happens is that you'll get like a strong contraction, and then but those motor fibers actually fatigue much faster, and so then you'll get fatigue onset much more quickly than native muscle physiology. So there are people doing research to figure out how to deal with this issue of reverse recruitment so that you're able to mitigate this issue of fast fatigue. In the lower extremity, it's particularly an issue. In the upper extremity, not as much. If the muscle fatigues, it's not going to respond as well to electrical stimulation. And so this is, and then when we connect it to the BCI or BMI, the arm may not respond in the way that the user is intending. So fatigue is definitely something that we keep an eye on and figure out ways to mitigate and things of that nature.
So the electrical stimulation in their sleep, is that also engaging both levels, or just that? What did you say the two levels were again? Of the recruitment.
Right. So electrical stimulation in the sleep essentially it essentially just exercises the muscle, right? So it basically sub-threshold.
Reminds me of one of those.
So I was thinking about whether or not I should use that analogy, right? So so what is it, like midnight shopping? Home shopping network,
right on the shopping.
Six-pack abs or something like that.
Abs and
So
that's one of our sponsors, actually.
Right. Number one, don't buy it. Right? Don't buy it. But in theory, it works because what you're essentially doing is you're basically causing the muscle to contract and basically exercise, right? We do that in these individuals to basically increase resistance to fatigue. It works to some degree. It's not going to give you 6 or 12 or 8-pack abs or whatever.
Damn, I was getting real excited about that research.
Right. But again, that will increase muscle tone, muscle strength, so that when we do connect it to the BMI, the arm will respond in the manner the user is intending.
So the user, or rather the patient population that you're focusing on, does that end up being primarily veterans, or what's the breakdown here?
Yeah, that's a good question. So veterans, I believe the numbers are only comprise about 11% of the general population, but they comprise about over 25% of people living with spinal cord injury, right? So veterans and the federal government have a unique interest and fund a lot of our research in terms of trying to advance these neuroprosthetic devices to help veterans and civilians regain some level of functional independence. Our work, we've had a number of participants in our studies, some of whom have been veterans, some of whom have been civilians. The VA Medical Center is a strong proponent and funder of our research, as is the Department of Defense, because again, they're interested in helping veterans who have sustained injuries regain some level of independence and be able to be integrated back into society. But our work could benefit anybody who's living with spinal cord injury resulting in paralysis.
One of your main collaborators is the VA. Can you kind of talk about how that collaboration with rehab came to be, and some of the challenges in getting together this group of researchers to work on this project?
Yeah, for sure. So as I mentioned, the FES Center, Functional Electrical Stimulation Center, that I joined in 2008 has actually been at the VA. It's actually what we call a VA Center of Excellence. So it receives most of its operating budget directly from the VA, which allows them to support research and development of these neuroprosthetic devices to help veterans and others living with paralysis regain some level of function. So I was fortunate enough to join the VA in 2008 and then subsequently joined Case Western Reserve University in 2012 to continue this work. One of the really amazing things about Cleveland, and specifically the medical research community, is that there are many people focused on using neurotechnology or developing neurotechnology to help to address a wide range of neurological injuries and diseases. So this includes spinal cord injury that we're working on. There are people working on understanding epilepsy and ways to mitigate epilepsy, Parkinson's disease, a number of other neurological injuries and disorders. And so there is a strong clinical research community in Cleveland, and specifically in the area of neurotechnology and how to use neurotechnology to address a number of neurological injuries. And again, the VA is a big leader in that.
So when you arrived, there was already this really strong neuro-focused ecosystem there.
Absolutely. There's a strong infrastructure, strong ecosystem, people who've been developing neurotechnology to address, to be able to restore functions of the lower extremities. I mentioned functions of pelvic functions, so the ability to pelvic functions, and then also the upper extremity as well. So I was fortunate enough to be able to plug into that and then take it further.
And how is your experience working or being trained in Duke and basically led to your your experience now in Case Western Code? Can you compare them? And
Sure. So, I like to say that I had known that I'd wanted to go to Duke University ever since I was in 5th grade.
Oh, nice.
And the reason was college basketball.
Oh, yeah.
I was a big Duke fan. I wanted to go there because of college basketball. And then about 11th grade, I was like, oh, Duke is really expensive. I need a real reason to want to go. And then it turned out that at the time, they were top 3 in the nation of biomedical engineering. I was like, I think I want to go to med school, so we'll do that. And that'll be my excuse to go to Duke, if you will. But then, also wanted to go to medical school, but then realized very quickly that I enjoyed the technical aspects. I enjoyed the engineering. And so, BME definitely fit me. So when I was at Duke, the Duke BME program actually spawned out of their electrical engineering program. So it was really easy at the time to do a dual major in biomedical and electrical engineering. And that's what I did at Duke. And then also got a minor in computer science. And so, I really enjoyed, technical aspects, programming, signal processing was one of my loves. And so I wanted to go into an area where I could use that skill set to address problems of human health. So the strong BME community at Duke and continues to be a leader in BME. From there, I went to Northwestern, where I did most of my work in the Rehab Institute of Chicago, and in that time, I was focused on developing control algorithms for people to use dexterous prosthetic limbs. Most prosthetic limbs to date, that are myoelectrically controlled by muscles, are simply open and close. And the question is, if you wanted to give somebody more dexterous function, how would you do that? How would you be able to coordinate the recorded muscle activity, the EMG, electromyogram, to be able to have them control a highly dexterous, high degree of freedom prosthetic device? So I did that work at Northwestern, and then was able to come to go to Cleveland and then apply the knowledge that I developed and learned both at Duke and Northwestern to now.
And how was your experience? You did a little bit of an internship at IBM too. So how did that kind of tie into your overall career?
Sure. So when I was at Duke, they had a very robust internship, and I believe they even had a co-op program. Although I didn't do a co-op, but as far as the internship goes, I was fortunate enough to be able to be connected to a number of companies in the Research Triangle Park area and also beyond. So IBM was one. I believe I worked at Cisco Systems.
I saw Procter and Gamble
as well. They were just opportunities for me to see engineering in the real world, which I think is a really critical piece of engineering education, right? Just whether for undergrads or graduate students, being able to get out in the real world and see, just what it means to be in an engineering, setting or firm. And for me, actually, what it solidified is that I wanted to go to graduate school. So it's actually honestly what it solidified. It's like, okay, I enjoy working. I enjoyed my experience working in a company, but I think I had a general love for learning. There, when you're in that corporate environment, you have a specific job to do, and being in academia, it solidified that being in academia better suited me.
You like the freedom to research what you were interested in.
To go more in depth, right? And I do encourage all of the students, for example, in our program at Case, especially at the undergrad level, go do an internship, go do a co-op, just so that you may turn out that you find out that, hey, I enjoy being in the corporate world, or I think I want to stay in academia. It's no experience is wasted, right? And a number of our graduate students in our program actually also get the opportunity to do internships and things of that nature. And again, it just helps you better understand what the options and opportunities are, and then what best suits you. So it was definitely a great experience for me.
So by the time you got to Northwestern, you had a pretty good idea of what you wanted to study, or was there still some searching that needed to be done before you really found a home in BCI?
Yeah, so when I got to Northwestern, the Rehab Institute of Chicago was pretty prominent, and I was aware of the research that was going on there in terms of prosthetics. And so I definitely had an interest in that area, and I was fortunate to find an advisor who had funding to take on another student, and I was able to pursue that. When I finished at Northwestern, it was actually funny because I had, ever since I was a kid, I wanted to be an astronaut, And so when I finished at Northwestern, I actually had an offer to go to Houston to do a postdoc for a professor who was looking at bone density, bone formation in microgravity environments. And that's actually what I was going to do as a postdoc, and it was really my excuse to become an astronaut. To go to space.
Get your foot in the door.
But consequently, I've actually learned that I'm glad that I was not an astronaut, because that feeling of your stomach in your astronauts have it all the time, and I hate that feeling on roller coasters and things like that. So I'm glad that didn't work out. But then when that fell through, my advisors pointed me to work that was going on in Cleveland, where they were looking at using brain-machine interfaces in connection.
Okay, now start
Recording.
3, 2, 1, go.
So how has the technology that the BCIs themselves changed over your course of when you started working in the field to now?
Yes, so the hardware itself hasn't really changed that much, which is, perhaps a little bit unfortunate. When I first started, the BlackRock microelectrode array was the only FDA-approved device for chronic implants in human participants. And the device has allowed us to push the field forward, and so we're very grateful to that company. In the last several years, there have been other companies which have gotten into the BMI field and have developed devices which are either close to or have gotten FDA approval for human. If I start with some of it, I'm excited to see those come online.
3, 2, 1.
What they allow the field to do. Some of the advances in the field have really focused on the algorithms that we use to decipher intention from the brain, and these algorithms have allowed us to decode movement, have allowed a number of labs to show that you can decode speech even, and so that's where a lot of the advances over the last 15 years have been.
And has so in terms of algorithms, how does AI play into some of the work that you're doing, and how has that revolutionized the field as of late?
Sure. So most of the algorithms to date have been what we call linear filters. They essentially take the activity of neurons and map them through linear equations to some desired output, whether it be movement direction or movement velocity. And furthermore, these algorithms to date typically have been developed for a single individual. There are questions about, how do we transfer these algorithms from one individual to another? What are the consistent patterns of neural activity that are consistent from one person to another? How do we develop nonlinear algorithms, if you will, to that are more
From
advanced
there,
than these
yeah.
algorithms?
Yeah.
So this is where machine
Alright.
learning comes
3,
in.
2,
We're generating
1,
terabytes of data every day. So there's always been a question about how much information is needed from the brain to be able to control a device, whether it's two-dimensional cursor or a high degree of freedom robotic arm. I think many people think that you need lots and lots of neurons. The devices we implant, at initial implantation, we're recording from about 100 or so neurons, and over time that actually degrades over time. That actually degrades because of neuroinflammation or other things as to neurons sometimes will migrate away from the implantation area. But there have been papers which have shown that even years, 3, 4, 5 years after implant, with just a few quality neurons, people can still control three-dimensional robotic arms to perform basic reach to grasp tasks. So I think that was a surprise maybe to people. The other positive surprise is that it's been shown that individuals from day one after receiving these BMI implants, they can actually use them to control simple cursors on the first day.
Really?
And again, that was a positive surprise. Even our participant where he was controlling not a cursor, but his own limb. He could do it on the first day, the first time we tried it. Now, of course, there is learning which occurs after the fact, and learning from the participant, and then learning about our algorithms, refining them. But with just the appropriate biofeedback or visual feedback, individuals can learn to modulate their neural activity on the first day to perform a meaningful control, and that was a positive surprise, if you will, in the field.
That's incredible to hear. And how does the way that people perceive these technologies change as they become users? Like, are people initially pretty skeptical?
That's a good question. So there was a survey done in 2015 out of Stanford where they surveyed people with spinal cord injury and asked them whether or not they would be willing to use an implanted BCI or BMI, and the survey respondents basically said yes. These are people with paralysis, living with paralysis, and they said that yes, they're willing to go through the process of being implanted with a BCI or BMI and use it so long as there is a significant benefit, over non-invasive methods, right? And so that's been the charge, if you will, to the field, to show that there is a real functional benefit to using these BMI systems. Our users, the people who've enrolled in our study, they from the beginning, they were not just excited about the technology, but also excited about their own ability to contribute to advancing the technology and science. And then, of course, they've seen some personal benefit in being able to use the BMI system to control their own limbs. And they've been a critical piece in terms of being able to develop the technology and advance the field.
But so it makes sense that the users themselves seem pretty optimistic about the technology. Are there any studies as to what the general population thinks about technologies like this?
So I don't think there are any formal studies, but the internet is a great but also dangerous place. Right?
Yeah.
And so there have been a number of times in my career where we've gotten media attention related to our work, and then one of the worst inventions in mankind is the comment section.
Oh my gosh!
Right? And so you'll see comments as to what people will make, and some of them are reasonable, but then there are others that people think that these technologies are the government's way of being able to read your mind and control your thoughts. That's really not. That's really not it, and maybe Hollywood has made that line of thinking popular, but really the technology that's being developed is a medical device, for and our purposes, a medical intervention to address a medical need. I think there is a segment of the population that understands that, but of course, there's a segment of the population which has fanciful ideas as to what this technology could be used for. And initially, when I started my career, I tried to avoid those conversations because they didn't seem grounded in responsibility or in fact. The conversation is being had, and now I think it is important for scientists to be a part of that dialogue, to be able to talk about the ethics, the facts, what the technology can actually do, such that the public discourse is one that is grounded in truth, as opposed to being off the hinge, if you will.
Yeah, so this is actually a very good segue into talking about your 60 Minutes interview, which
Sure.
you have done. So this is not the first podcast that you have done necessarily.
Sure.
So,
Right.
how has that kind of exposure to the public helped your day-to-day research, your lab's functioning? You could talk about that.
Yeah, so the 60 Minutes experience was an experience. It was an amazing experience. We started talking, I think it first came out in March of 2023, but we started talking to them in May of 2022. And they were it was an amazing journalistic experience. They were very thorough. We had an opportunity to meet Scott Pelley, who was the correspondent, and he had an opportunity to meet our team and meet our study participant. And they did an amazing job. Interestingly enough, Mr. Pelley had actually 10 years prior done a previous segment on BMIs where they interviewed, I think, University of Pittsburgh and other groups that were using BMIs to control robotic limbs. So this was sort of a 10 plus year follow up for CBS at 60 Minutes. It was a great experience. Since that time, one of the things that it did is it gave us greater exposure of our work to people across the country. I've had a number of people, call us up and ask if they could enroll in our study.
Wow.
And it's been a mixed bag, because usually, unfortunately, the answer is no for a number of reasons. We have very strict inclusion-exclusion criteria. Some people had afflictions which were not consistent with the application of the technology, and so we have to humbly and sadly tell them that there's not a lot that we can do for them. Other people, their logistics in terms of where they're located. We've had people in other countries, ask us if they could join our study. Because our study right now is limited to a small radius in the Cleveland area, we haven't been able to extend to those people. But again, it has given our work exposure, and the hope is that we'll be able to expand the reach and the footprint of our work to be able to go well beyond Northeast Ohio, the Cleveland area, and especially as we start moving the system away from being a research in the lab system to something that could potentially be take home. This will then increase the possibility of expanding reach.
Can you kind of talk about how the affliction dependent criteria would exclude somebody? Is it maybe they're not the lack of use isn't prolonged enough, or what are the criteria here for the
Yeah. So there, in terms of somebody who has a spinal cord injury, some of the inclusion-exclusion criteria relate to the length of time post-injury, right? So after spinal cord injury, in what we call the acute phase, so which is defined from 0 to about 6 months, there's actually continued healing of the injury to some degree, such that you could see an injury, somebody's injured at the cervical level 2 region, move down to functionally being a cervical level 3 or 4. So we want to wait for that process, that acute phase to end, before considering them to receive any sort of a neurotechnology intervention. So one of our exclusion criteria is that anybody, I guess in this case was less than a year, would not be a candidate for our study. So a year out or 9 months out, 9 months after the fact, they could be part of our study. Because we are not just looking at the BMI neurotechnology, we're also looking at FES, of functional electrical stimulation, to restore arm and hand movements. We are interested in the individuals who have the most severe cases of tetraplegia, of paralysis. And so if an individual has too much function, they may not be a candidate for our particular study. Now, they could be a candidate for other studies, looking at maybe just hand restoration if they have retained arm function. But for the particular study that we're running right now, the rehab study, our focus is on restoring hand and arm function, and so we're looking for people who have the most severe cases of paralysis. So for somebody with spinal cord injury, those would be some of the most immediate inclusion-exclusion criteria. There are a number of other things related to whether or not they're on a ventilator, or whether or not they need to be able to have an MRI, because the devices are not MRI compatible. They could not get an MRI after getting our implants. Whether or not they've had any sort of some comorbidities, whether or not they've had any sort of cardiac issues or prone to seizures. These are some of the things that we look at, and because at the end of the day, we want to make sure that the device would not cause additional health risk to the individual. So those are some of the inclusion-exclusion criteria. And then there's some logistical things in terms of how far they are away from our center.
And is it so usually participants of these studies, do they have these systems put in place during the duration of during a set duration and then taken out essentially?
That's a really good question, and there's ethical questions to be asked about that. So our study, the maximum as this point in time that an individual will be enrolled in the study is 6 years. Okay, we haven't had anybody actually reach the end of that time, but in addition, people at any time could leave the study. Now, what does that mean for somebody to leave the study who has an implant? It's a question of, would the device get taken out. We do encourage individuals to get the devices removed for safety reasons if they're no longer part of the study, but everybody has autonomy over their own body. They can make that decision on their own. There in these discussions, if you ask people with these devices, one of the things that I have heard said is that if a device is removed from an individual who, let's say they had paralysis, they gained some function with this neurotechnology, and then you remove the neurotechnology from them again, some individuals have said it feels like they've been injured all over again. And the question is, what do you do with that, right? So the center that I'm a part of fortunately has a great history of supporting legacy devices, because it is a real question. Is if your research is grant supported, and then the grant is over, and you're not under the guise of a company, how do you continue to support individuals who've given their time, given their energy, gone through great risk to help advance the technology? Fortunately, our center has a decades-long history of supporting legacy individuals or with legacy systems. There is a real question as to what is the right model, and I don't think anybody has a real answer for that yet. If a study is over and the device is not supported by a company, what do you do? In extreme cases, there was actually a company who shall remain nameless. I'm sure people can look it up, but where the company went out of business and they were looking at restoring, they were developing retinal prostheses. And the company's out of business, and there are individuals with these implants that are no longer supported by the company because the company's out of business. What do you do? What do those individuals do? So there are
whose responsibility
who's
is that?
responsible, right? Those questions are the sort of questions that are still remain to be answered, and there are lots of smart, bioethics people, people in the legal system, scientists who are trying to figure out, the right way to address those concerns.
For legacy systems like that, how does that support process look? I mean, are they essentially having to stockpile replacement parts, or what's the protocol there? Is there a certain duration of time where they allow that support for?
The answer is there is no answer.
Okay.
There is no defined protocol. Really, it's the fact that the people in our center are just fundamentally good people, and so over time it's harder and harder to find the same parts, but they do their darndest to find the parts and to support the legacy systems, and these individuals who've again given their time and their energy to helping develop the technology. Now, this can't go on forever, right? And it's unclear what the right model and answer is, but these are things that people are discussing now. So.
And it's at least good to know that there's support that's being offered to these systems in some form.
In some form,
because we as graduate students have very much experience having to deal with
old equipment that isn't supported,
and it definitely puts this situation in a whole other light now.
Absolutely.
It's really great to see the advances in research that you're making. I mean, you're impacting directly people's lives who've gone through these extremely traumatic events. And, it's February. It's Black History Month.
Sure.
You're an incredible Black scientist.
Thank you.
Can you kind of speak to your experience as a person of color in the science and engineering space?
Sure. So, I think at the end of the day, it's the human experience which connects us, right? And I've been fortunate enough, I understand it's not necessarily the experience of everybody, but I've been fortunate enough in my career to have mentors who cared about me and who were not just mentors in the sense of mentoring me through a research experience, but also sponsors. And by that, what I mean is that they were willing to put up their, capital, whether it's political capital, financial capital, to promote me and the work that I was doing. And so I've been fortunate to have excellent mentors who cared about me personally, right? I feel like, my role now, as somebody who's, been able to, navigate those waters is to then create opportunities for others as well. And so, my lab in particular, is quite diverse in terms of the students that we recruit. One of the things that we also try to do is have our study study participants or patient population be diverse as well. There is unfortunately a poor history of science in terms of things that have been done to underrepresented minority populations, and so there potentially is, and not even potentially, there is oftentimes a distrust from underrepresented minorities about science. My hope is that being able to demonstrate some of the benefits of our work, and as you see more underrepresented minorities in the sciences, that we can reach out to those communities and show how these communities can also benefit from scientific advances. So that's one of the major goals of my lab and my work as well. I think ultimately you create environments where people can see people like them that have been successful. That ultimately is as a magnet will attract more people to say, hey, it is a real possibility to be a person of color and be successful in the sciences and academia. My hope is that I can play a small role in that process.
Thank you, Doctor, for giving us your time and
My pleasure.
visiting us here in New Orleans. It was a pleasure to have you on this podcast.
Excellent.
And if there's anything you would like to tell our audience, to either about your research or anything that you want them to know at the end of this, please.
Yeah, no, I'm incredibly grateful for the opportunity to be here. I've been impressed by you two and the amount of
Thank you.
Effort that you guys have put and research that you've done into me, and just this opportunity to talk to you guys and come to New Orleans and see Tulane. Very impressed with the environment, so thank you for having me.
Thank you so much.
Thank you.
All right.
Thank you.
Thank you.
Thank you.
All right.